Okay, the compound A with the molecular formula C4H9Br. Okay, right up. So it is undergoes what? Yeah, it is treated with the aqueous potassium hydroxide. Whenever you see aqueous potassium hydroxide, okay, whenever you see aqueous potassium hydroxide, just remember it is a substitution reaction. Okay, so this compound undergoes substitution reaction, nucleophilic substitution reaction, because the OH, okay, the KOH, when it is dissolved in water, to provide a OH minus, it is act as a nucleophile. Okay, nucleophile. So the nucleophilic substitution reaction takes place. Nucleophilic substitution reaction takes place. Okay. So at the same time, what is the rate of the reaction? The rate of the reaction is directly proportional to the concentration of the substrate A alone. So definitely it is a first order reaction. So it is considered as a nucleophilic substitution unimolecular. Okay, nucleophilic substitution unimolecular reactions. Okay, right on. Then so from this, what you learn, what is your conclusion means? Definitely the SN1 reaction is favorable for tertiary compound. So the given molecular formula, by using this given molecular formula, you can construct the tertiary compound. Okay, so totally 4 carbon atom. So take 1 carbon atom. Here bromine is a active group. Okay, Br. So remaining 3 carbon atoms you can write like this. So you will get a tertiary alkyl halide. Okay, tertiary butyl bromide you got. Okay, CH3, CH3, CH3. Tertiary butyl bromide. Okay, so it is favorable for SN1 mechanism. Okay, that's why when it is treated with the KOH, what happens? Aqueous KOH solution, the bromine is substituted by OH group. So nucleophilic substitution reaction is called. Okay, CH3, CH3, okay, OH plus KBr, this is your product. So from this tertiary butyl bromide, you will get a tertiary butyl alcohol. Okay, so it is a nucleophilic substitution reaction. Because of tertiary compound, it is follows SN1 mechanism. Okay, it follows what? SN1 mechanism. Okay, the same compound, it should be optically active. Okay, right, the same molecular formula. Okay, but it shows a different structural formula. But the compound B, another one structural formula is formed. Okay, that is called the B. The compound B is optically active. Optically active. Okay, it is optically active. Therefore, what happens? By using this formula, you have to form an optically active compound. Already, you know, optically active. We have 3 important points. Okay, the substance should contain chiral carbon. Okay, right? It should not mirror image. Okay, it's not superimposable with its mirror image. Absence of a plane of symmetry. These are the important criteria for optical activity. Okay, so here optical activity, based on the given formula, you can form a active center, that is chiral carbon centers. Okay, so by using this molecular formula, okay, so carbon, okay, so totally 4 carbon atoms. Okay, right? So here 1 carbon atom should be chiral carbon. Suppose if you take this one, okay, so here one CH3 group is there, here CH2 CH3 group. Okay, here 1 hydrogen you can place. Okay, here you can put bromine. So this central carbon atom, this carbon atom is a chiral carbon atom. Why? Because it is surrounded by 4 different groups. 4 different kind of groups. Okay, so CH3, CH2 ethyl group, here methyl group, here 1 hydrogen, here 1 bromine, bromo group. Okay, because of this reason, it is considered as a chiral center, chiral carbon. So it is optically active. Okay, it is optically active. So optically active form of compound B, structure be like this. Okay, so actually it is a secondary alkyl halide. So it is favorable for SN2 mechanism. So SN2 mechanism, the rate of the reaction is directly proportional to what? Concentration of the reactant B as well as concentration of the reagent used. Okay, we are using aqueous KOH, nucleophile. Okay, so the rate of the reaction is directly proportional to concentration of the reactant as well as concentration of the nucleophile used, KOH. Okay, so The rate depends upon the both the concentration. Definitely it is a SN, which follows SN2 mechanism. That's all. Okay, so which one is optically active, which one is optically inactive, which one is undergoes SN1, which one is not undergoes SN1, which one is favorable for SN2. Okay, right? Which one is depends upon the concentration of the reactant alone, which one is depends upon the concentration of the reactant as well as reagent. Okay, based on that you can find out A and B like this. Okay, right? That's all.